Zoom session is being brought to you by the Fractal Octaves Z. All right, today we go through complex numbers and 3-6 complex roots and the fundamental theorem of algebra. All right, complex numbers, they're sort of the next step in the development of the number systems. I mean, originally it's call a number, people call numbers like 1, 2, 3, 4, 5, and so on, counting numbers. Then someone added in zero and the negative numbers, so you can always do subtraction. Then you add in the fractions, so you can always do division. And then limits, so you can find square roots. And then here, taking square root of a negative number. Let's call I the square root of -1. Its square equals -1. The trouble is, you see, is if you take a positive number, that squared is positive. 0 squared is 0, negative squared is positive. None of them yield a negative. So whatever this I is, it's neither positive, 0, nor negative. So it's nowhere on the real number axis, number line. So, okay, therefore they called it an imaginary number, which is sort of an insult in a term. Mathematicians do that a lot. Irrational numbers, whatever. Okay, so finally, one day somebody said, well, you know, if it's not on the line, let's put it off the line. In fact, 90 degrees off the line is part of a plane. It's a sideways unit, in effect. And okay, if you go on and talk about numbers like a plus I times b, then it's on a number plane where you move over a and up b. So a units along the real axis, a is the real part. B units perpendicular along the imaginary so-called axis, called the imaginary part. Between you and me, I would really prefer, instead of calling them positive, negative, and imaginary units, Gauss said he'd rather call them direct, inverse, and lateral units, but whatever. Okay. The idea is that these so-called complex numbers are really planar numbers. And the idea is you want to invent some way to operate with these things. In fact, treat them like numbers. You want to add them, subtract them, multiply them, and divide them. This set of plane of numbers is called complex numbers. It's denoted by this Fraktur, German, gnarly German letter C. Okay, we wanted this definition to be arithmetical. We also want to have a geometrical interpretation in order to justify identifying them with points on a plane. Okay, first, for adding complex numbers, a plus ib plus c plus id. Basically, you act as if the usual laws of arithmetic work, so that you can shuffle numbers around, move parentheses around, reverse order, and so on. So you have a plus c, and ib plus id, and remove a common factor of I, get I times b plus d. So it's a plus c plus I times b plus d. So you add the real parts and the imaginary parts in parallel. Okay, so just two additions. That's simple enough. And interpreted geometrically, it's like this. Here's a complex plane with the number 0 at the center here. If this is a complex number z and this is number w, you draw this line here and this line here. And you draw this line parallel to 0z, and this line here parallel to 0w, and they meet here at this point here, and we call that z plus w at the other end of the parallelogram. And that's the same w as defined this way with the arithmetic method. So this is called the parallelogram law. So you add the components in parallel, and the added sum is the furthest point of a parallelogram. That's simple enough. A plus ib minus c plus id, well, you subtract the imaginary and real parts. A minus c plus I times b minus d. Okay, now here the idea is this. If this is complex number z, this is complex number w, then minus w points in the opposite direction. Same length, opposite direction. And you add z and w, negative w to here to get z minus w. I've nicknamed this the D rule. D for difference, and you can see a letter D here, lowercase d. Now, to multiply in complex numbers, we use FOIL, first, outer, inner, last, and the rule that I squared equals -1. As ever, we're basically treating these as if they were like the old numbers with the same rules, but with this additional thing here. So, okay, a plus ib times c plus id. First is ac. Outer is a times id. Inner is I times bc. Last is IB times ID. Well, okay. All right, now so AC plus I squared BD. These have a common factor of I times AD plus BC. Oh, and then you remember that I squared is -1. And so A plus IB times C plus ID is AC minus BD plus I times AD plus BC. Okay, this is a formula, and you can memorize it if you wish. I think it's just easier to just use FOIL and I squared equals -1. So 5 plus I times 3 plus I times 2. Well, 5 times 3 minus 3 times 2 for the real part. I times 3 times 3 plus 5 times 2 for the imaginary part. 15 minus 6 plus I times 10 plus 9 is 9 plus I 19. Oh, by the way, a minor issue. Here I'm writing A plus IB. Sometimes the book will have it A plus BI. Either way, really. It's commutative. It doesn't really matter which order you write them. I prefer to put the I in front, however, because I consider I to be less like a number than like a sign, plus minus I. Oh, now here's a fun one. A sum, 5 plus I3, times a difference, 5 minus I3. Okay, if you multiply it out, what will happen is that the I3, I times 3 times 5, and the minus 5 times I3, here and here, they cancel. So it has no imaginary part at all. What's left is 5 times 5 minus I squared 3, but minus I squared is plus. You get 25 plus a 9 is 34. In general, if you have a number, A plus IB, complex number, times this other number, A minus IB, you multiply it out, the imaginary part, AIB minus AIB cancels, and the term I squared B squared minus I squared B squared becomes a plus B squared. So number times this thing called a conjugate equals A squared plus B squared. These two numbers, A plus IB and A minus IB, are what are called conjugates. If A plus IB is up here in the complex span, A minus IB is reflected through the real axis. So number times conjugate equals sum of squares. For example, 3 plus 4i times 3 minus 4i is 3 squared plus 4 squared, which is 9 plus 16 is 25. 7 minus 2i times 7 plus 2i is 7 squared plus 2 squared, 49 plus 4 is 53. Now this is useful for dividing complex numbers. You have 1 over 3 plus 4i, multiply above and below by the conjugate of the denominator. 3 plus 4i times 3 minus 4i is 3 squared plus 4 squared, or 25. 1 times 3 minus 4i is 3 minus 4i. So you get 3 minus 4i over 25, and then you split it up to 3 over 25 minus I times 4 over 25. So that's the reciprocal. Here we have a division. 1 plus 3i over 7 minus 2i. We'll multiply above and below by the conjugate of the denominator, 7 plus 2i. In both cases, we rescale the fraction by the conjugate of the denominator. All right, now, 7 minus 2i times 7 plus 2i is 7 squared plus 2 squared, 49 plus 4, so a 53 in the denominator. In the numerator, well, okay, 1 times 7 is 7, 3i times 2i is minus 6, 3i times 7 is 21i, 2i times 1 is plus 2i. After a bit of arithmetic, you get 1 plus 23i over 53. And, okay, breaking into real and imaginary parts, it's 1/53 plus I times 23/53. All right, here's some examples. 7 minus I times 9 plus 3i. What's that? Well, we add the real parts. 6 plus 9 is 15. You add the imaginary parts, -1 plus 3. That's 2. And so you get 15 plus I times 2. 7 minus 3i minus 4 plus 2i. Okay, you subtract the real parts. 7 minus 4, that'll be 3. Subtract the imaginary parts, minus 3 minus another 2, so -5. So you get 3 minus I times 5. 2 plus I times 3 minus I. Okay, do FOIL. 2 times 3 first, outer is minus 2i, inner is plus 3i, last is I times -I, which is minus a -1. plus I times minus I. The negatives cancel, I get a plus 1. So 6 plus 1 plus I times 1 is 7 plus I. And here we have the square of 2 plus I. Well, 2 plus I times 2 plus I. 2 times 2 minus 1 times 1 for the real part. 2 plus 2 for the imaginary part. And you get 3 plus 4I. Here we have 3 minus 2I over 4 minus I. Okay, to divide fractions, we multiply above and below by the conjugate of the denominator. In this case, 4 plus I. 4 minus I times 4 plus I is a squared plus b squared. 4 squared plus 1 squared. The numerator, after a bit of arithmetic, is 14 minus I5. That over 16 plus 1. And a bit more arithmetic gets you 14 over 17 minus I times 5 over 17. 5 plus 9I over 1 minus I. Multiply above and below by the conjugate of the denominator, 1 plus I. And okay, 5 plus 9I times 1 plus I. 5 times 9, 5 times 1 minus 9. 9I times I is a minus 9, so 5 minus 9 for the real part. 9I times 1 plus I times 5 is 5 plus 9 times I. The denominator, a minus bi times a plus bi is a squared plus b squared. In this case, 1 squared plus 1 squared makes 2. Underneath, negative 4 plus I times 14. And a bit of arithmetic, minus 2 plus I times 7. Here we have the square of a complex number. So you have 4, well, okay, I may as well use the usual rule, which is the square of a difference is a squared minus 2ab plus b squared. That's another way to do it. So 4 squared plus 2, minus 2 times 4 times 8i, and plus the square of 8i. That's 4 squared is 16. Here in the middle is minus 64i. 8i squared is 8 squared, 64 times I squared, negative 1, so negative 64. And then 16 minus 64 is a minus 48. So the net result is minus 48 minus 64i. Here I have the cute one. One of these alternate, same problem in 2 different ways. Here's the square of 2 times I, and here's the square of 2 plus I. What are they? Okay, the square of 2 times I, you distribute the square like you do with real numbers. 2 squared times I squared. I squared is negative. 2 squared is 4, so a negative 4. 2 plus I squared, well, okay, a sum of a square of a sum is square plus twice product plus square. So 2 squared plus twice 2 times I plus I squared. So it's 4 plus 4I minus 1, or 3 plus 4I. All right.